They called it backward, a locomotive running in reverse. Engineers said it would kill the crew in the first collision. Railroad inspectors predicted catastrophe. Industry magazines published editorials condemning the design as reckless, dangerous, an abomination of engineering common sense. Then crews started surviving tunnel runs that killed men on conventional locomotives, and the backward design became the only machine capable of crossing the Sierra Nevada without suffocating its operators. The Southern Pacific cab forward, and the locomotive that ran with its boiler behind the crew instead of in front of them. Critics said it was suicidal. They were wrong. The problem wasn't the locomotive, it was the mountain. The Sierra Nevada presented American railroads with a challenge unlike anything else on the continent. Steep grades, tight curves, and tunnels. Miles of tunnels bored through solid granite, yet including the infamous Donner Pass route that climbed from Sacramento to the Nevada border through 40 tunnels and snow sheds spanning over 15 miles of mountain terrain. Conventional steam locomotives handled the grades adequately. They could pull freight over Donner Pass if enough power was applied, but the tunnels were killing crews. Steam locomotives produced enormous amounts of smoke and exhaust. In open air, wind dispersed it quickly. In a tunnel, smoke filled the bore, concentrating gases that included carbon monoxide, sulfur dioxide, and superheated steam. Temperatures inside tunnel-bound locomotive cabs reached 140 degrees Fahrenheit. The air became unbreathable within minutes. Crews operating through Donner Pass tunnels faced a deadly choice: breathe the toxic air and risk passing out, or hold their breath and risk making a fatal mistake at the controls. Neither option was sustainable. Tunnel runs averaged 10 to 15 minutes of continuous exposure. No one could hold their breath that long. Everyone who breathed the air suffered. And engineers developed symptoms ranging from headaches and nausea to complete loss of consciousness. Firemen, working directly behind the firebox where smoke was densest, had it worse. Some collapsed at their posts. Others staggered to the rear platform seeking fresh air, abandoning the fire and causing the locomotive to lose steam pressure mid-tunnel. Trains stalled. Rescue operations followed. Men died. Southern Pacific management knew they had a problem. Between 1900 and 1910, multiple crew members suffered serious injuries or death from smoke inhalation on the Donner Pass route. The railroad tried various solutions. Ventilation systems installed in tunnels helped but couldn't eliminate the smoke. Respirators were issued to crews, primitive cloth masks soaked in water. They were uncomfortable, interfered with breathing, and provided minimal protection. Most engineers refused to wear them. The railroad considered electrification, eliminating steam locomotives entirely on the mountain crossing. The Pennsylvania Railroad had done exactly that through the Hudson River tunnels in New York, replacing steam with electric locomotives to avoid the smoke problem. But electrification required massive capital investment. Millions of dollars for catenary wire, substations, and new locomotives. Southern Pacific didn't have that budget for a single mountain crossing. What they had was California oil. Cheap, abundant petroleum from fields around Bakersfield and Los Angeles. Oil-fired locomotives produced less smoke than coal burners, but they still produced exhaust, and the tunnel problem remained fundamentally unchanged. Burning oil instead of coal didn't move the crew away from the smoke. Moving the crew required moving the cab. The idea wasn't entirely new. A few experimental locomotives in Europe had placed the cab at the front of the machine for better visibility in switching operations. But no one had built a large, powerful, mainline locomotive with the cab forward specifically to solve a smoke problem. Southern Pacific was about to try. The design challenge was significant. A conventional steam locomotive had the firebox at the rear, the boiler in the middle, and the smokestack at the front. The crew sat behind the firebox where they could tend the fire and monitor steam pressure. Reversing this arrangement, putting the crew in front and the boiler behind them, meant the cab had to be at the very front of the locomotive, ahead of the cylinders, ahead of everything. This created obvious problems. In a collision, the crew would be in the point of impact. Yet conventional locomotives had the massive boiler between the crew and any obstacle. Cab-forward designs put nothing between the crew and disaster except the front buffer beam and a few inches of steel plate. Critics focused on this vulnerability. Editorials in railroad trade journals called the design a death trap. Some compared it to putting engineers in the front car of a passenger train. Technically possible, but obviously insane. The conventional wisdom was clear. Crew safety required mass between the operator and the impact point. Removing that mass was suicidal. Southern Pacific engineers countered with data. Collisions on mountain grades were rare. The territory where cab-forwards would operate, the Sierra Crossing, had minimal traffic, controlled by absolute block signals that prevented trains from occupying the same section of track. Head-on collisions on single-track mountain railroads happened primarily due to dispatching errors or signal failures, both of which were preventable through proper operating procedures. Smoke inhalation, by contrast, was a daily, routine hazard. Every tunnel run exposed crews to toxic gases. The cumulative health effects were measurable and severe. Trading a theoretical collision risk for an immediate documented health hazard made sense, if you trusted the numbers. Southern Pacific's chief mechanical engineer, A.D. McDonald, trusted the numbers. In 1909, he oversaw construction of the first cab-forward prototype, a massive articulated mallet-type locomotive designated MC2. The cab sat at the very front of the machine. The firebox and boiler followed behind. Yet the tender, carrying fuel oil and water, trailed at the rear. The entire locomotive was 106 feet long and weighed 485,000 pounds. The articulated design was critical. The locomotive's frame bent in the middle, allowing it to navigate the tight curves of the Sierra Crossing. The front engine drove one set of driving wheels. The rear engine drove another. Total tractive effort, over 100,000 pounds, enough to pull heavy freight over Donner Pass without assistance. Operating a cab-forward required relearning basic locomotive handling. The engineer sat facing forward, but the boiler extended behind him. Visibility ahead was excellent, better than any conventional locomotive. Visibility behind was non-existent. The fireman, stationed in a second cab just behind the engineer, tended an oil-fired burner that required far less physical labor than shoveling coal. Communication between the two crew members was easier than on conventional designs. They were only a few feet apart instead of separated by the length of the boiler. The first test runs through Donner Pass tunnels validated the concept immediately. Smoke vented behind the locomotive, away from the crew. The engineer and fireman breathed clean air throughout the tunnel run. No headaches, no nausea, no loss of consciousness. The cab temperature, though warm from the California sun, stayed well below the 140-degree inferno of conventional locomotive cabs. Crew acceptance was swift. Engineers who had dreaded tunnel assignments on conventional power volunteered for cab-forward runs. Word spread through the division. The backward design wasn't deadly. It was the only safe way to cross the mountain. Southern Pacific ordered more cab-forwards. Between 1910 and 1944, the railroad built or purchased 256 cab-forward locomotives in various classes, all designed for mountain service on oil-burning territory. They operated primarily on the Sierra Crossing, but also saw use on other California mountain grades where tunnels and smoke were problems. The design's advantages extended beyond smoke elimination. Forward visibility allowed engineers to see track conditions, signals, and obstacles much earlier than on conventional locomotives. This proved valuable in snow country, where avalanches and slides could block the track without warning. Cab-forward engineers had seconds more reaction time, often enough to stop before hitting an obstruction. While the feared collision vulnerability never materialized into the catastrophe critics predicted. Cab-forwards operated for over 40 years without a single crew fatality attributable to the forward cab position. The locomotives were involved in accidents, derailments, mechanical failures, the usual incidents that affect any machine operating in difficult terrain. But the cab placement didn't increase crew casualties. If anything, the improved visibility prevented accidents that might have occurred with conventional power. But the design did have limitations. Cab forwards were purpose-built for specific territory. They excelled on mountain grades with tunnels and curves. They were less useful on flat main lines where smoke dispersal wasn't a problem, and the forward cab offered no advantage. Southern Pacific never attempted to use them system-wide. They remained specialized machines for specialized service. Maintenance presented unique challenges. The articulated frame required careful adjustment to prevent binding. So, the oil firing system needed regular cleaning to prevent burner clogging. The forward cab, exposed to the elements, took more weather damage than conventional locomotive cabs tucked behind the boiler. But these were manageable problems. Southern Pacific mechanics developed expertise maintaining the fleet, and operational availability remained high. The cab-forward era ended with dieselization. By the late 1940s, diesel-electric locomotives offered better fuel economy, lower maintenance costs, and, crucially, no smoke problem at all. Southern Pacific began replacing steam power across the system. The last cab forward made its final revenue run in 1956. Most were scrapped. A handful survived in museums, preserved as examples of engineering innovation driven by necessity. The backward locomotive that critics called deadly had proved them wrong by saving lives. Not through superior collision protection, that was never the point, but by solving a real, immediate problem that conventional designs couldn't address. And the cab forward demonstrated that engineering orthodoxy, crew behind boiler always, could be challenged when conditions demanded it, and that sometimes the backward way was the only way forward. Oh, abo, bambin.